So our next speaker is Steve Holloway from Dialog Semiconductors, where Steve is a principal verification engineer. Steve has 19 years experience of functional verification methodologies, including ERM, which always suggests the age of somebody when we know ERM, OVM and UVM, and functional property checking. He has led the verification of large-scale human SoC projects. He joined Dialog Semiconductor in 2007 and previously worked for Doulos, NXP, and Trident Microsystems. Steve would like to thank Wolfgang Mayerweiser for his... He's probably listening, so I might better get it right. Wolfgang Mayerweiser for his invaluable input into the presentation. Thank you.
Okay, thank you, Mike. So go back to the sort of title of the presentation. So really this making formal normal is a kind of user account of how we developed our expertise in formal within Dialog and some of the tips and tricks that we found on the way. So just for any of those who don't know anything about what Dialog Semiconductor is, or in the audience who haven't worked for us before, we're basically a company that provides mixed signal ICs with a focus on power management, power conversion, and connectivity. So what was Dialog's formal journey? Well, basically, without going into too much detail on these slides, our first sort of baptism of fire in formal was that we actually had a post-silicon bug a couple of days before a product which our chip was in was about to be launched. And if you can imagine, there was a huge amount of chaos and finger pointing and all the rest of it about what this bug was. It was an extreme corner case, and why we didn't find it in simulation, and could we use formal to find it, and could we then assure that the fix that we had proposed would actually mean that this bug wouldn't actually turn up in any instance in this product with a massive user base. So we actually went through a fairly rapid learning curve about formal due to this big issue that we had. But in terms of the way that we've adopted formal, you can sort of see on the left-hand side of the slide, it's a sort of knowledge acquisition process. Part of it is hiring, part of it is training, and part of it is then deploying the formal expertise in our projects. And as Harry Foster said earlier in the day, part of this is actually making sure that you consider formal very early on in your V-planning exercise. So we're using things like, as I said before, formal for post-silicon debug. Security, we actually had a particular requirement for making sure that there was essentially some security control in one of our devices, that there was no possible way to have the security feature triggered by any other source. So that was a very good use of formal. We were routinely using automatic formal analysis and the sort of superlinting features that you get in the formal tools. We also developed some in-house scripts and apps, we call them, for particular design structures that we have for some of the low power logic. So we have some sort of means to switch clocks on and off dynamically. So there's a regular structure that we can then design some scripts around it and say formally, has the logic been designed correctly so that when nothing's requesting a clock, then nothing needs to request a clock, then these clock request lines, the logic that goes into them is actually correct. So we have some in-house scripts for that sort of thing. And then we're also using formal property verification. This is a sort of user-defined properties. This is the sort of hardcore formal proofs, and then when you run out of steam, maybe you go to a bug hunting mode on that. So that's basically the story of how Dialog has sort of taken on the formal technology into our verification flow obviously for hardware design. So where does it fit into the verification flow in this sort of generalized picture? Well, sort of everywhere, really. So I think a key point here is that in the V-planning part of the process, then I think you need to make sure that you're actually targeting the formal verification features, and you're thinking about design assurance in terms of things that could never happen and things that must always happen. So those sort of properties are actually generally quite simple to write in formal and can be very powerful in terms of assuring your design doesn't do anything horrific. So it needs to be definitely considered in the verification planning flow. And then also in the RTL design part of the flow, then we encourage the designer to embed properties into their design so that they can be reused in the verification flow. They can check those. They can also use the automatic formal analysis and the sort of superlinting. They can look at dead code. They can look at reachability on a finite state machine structures. There's plenty actually of added value, and also the RTL designers are using these in-house scripts to make sure they design the low power logic correctly, and it triggers the various requests at the appropriate times. Then when it comes to the sort of the meat of the verification, then we're using the formal property checking, scripts and apps that we developed in-house to do that. So then we move on to coverage closure, the sort of end game of your verification activity. Then we're using the formal unreachability flow. So basically what that does is it allows you to pass a coverage database that you you've obtained from your constrained random verification, and then put that back into the formal tool, and then ask the question about how many of these coverage holes are actually reachable from a formal perspective. So is it worth then marking them off as unreachable and not pursuing them in simulation? Then we also have another tool at our disposal, which we call formal replay, which is a kind of reachability flow rather than unreachability, and it shows you from your uncovered part in your coverage metrics, which are actually reachable. It then allows us to essentially take some witness waveforms from the formal about how you can reach those, put those back into the simulation regression, and actually get our code coverage for those things. And then towards the end of the flow, we see that we've got this sort of, well, I haven't shown formal equivalence here, but of course we've got formal equivalence technology here between the RTL and the gate level, but then the post-silicon bug hunting and design assurance that you get if you have to make some ECO changes. Okay, so that's where it sort of sits. Well, basically the answer is it sits all over in the verification flow. Another sort of interesting picture to look at is how does the sort of timeline of developing a formal environment versus going through the building up and reaching closure in your simulation domain, how do they sort of compare and contrast? So if you look at the sort of top simulation flow, you tend to be front-loaded with a lot of build effort in your verification environment. So if you're building UVM environments, you've got a lot of heavy lifting in terms of building your infrastructure, your UVCs, your reference models, and whatever it is. So you tend to be building your test bench, doing some sanity checks, refining those models and checks, refining the stimulus, and getting into the really deep, fun debug towards the end of that. And then you move into your coverage closure mode. Whereas it's almost a reverse paradigm for the formal flow, because you're sort of, I've sort of characterized it as being a refinement effort here. But as you start to do the analysis on the design under test in the formal tool, you're straight away into corner cases and deep debug and conversations with the designer. So the formal tool, then you would basically take your initial environment and refine it in terms of the models checking constraints, reach some bounds. Usually almost certainly you'll reach some proof bounds where the tool runs out of steam. And then you'll have a sort of decision about, well, are we going to now stop in terms of formal foolproof? Are we going to then move into a bug hunting mode? And in some ways, the formal effort has to have some kind of time limits inside it, rather than having some kind of metric sort of limit as we would have in the simulation flow. So it's interesting to compare and contrast those. And in terms of sort of complementary activity, it's very good to start the formal even before you have a complete design, because you can actually improve the quality of that design whilst you're building the simulation environment. So this is the way that we see it goes. So what are some sort of tips and tricks and some sort of guidelines that we've sort of come across and that we adopt within Dialogue? Well, the first, I think, a very important point to make is when you're starting with formal analysis, that just think about covers, your formal covers. Don't leave them to the end. If you put in some formal covers for expected use case scenarios for your design under test, you will be able to then confirm to see if that specified behavior is possible in your environment. So it's very, very useful to see, and it's great for people that maybe don't know the formal technology very, very well. What you can do is you can put in some quite complex cover sequences, and you can look at the waveforms that you might have in your spec. So we'd have a recipe to say, well, okay, can we then put covers in for all our normal use cases, every waveform diagram that we have in the spec, all transaction types possible on the buses? Can we do FSM states and arcs? Are they reachable? That's normally part of the automatic analysis that we actually get for free with the tool. And then we move on to things like corner cases, FIFO, full empty, error, or bad machine cases. Can we actually cover those? So I think it's kind of, maybe it's not that clear in the literature or in a lot of stuff you read about it, but I think that this is a big common mistake that people start to get start to write the properties first, don't think about coverage, don't think about can they see the pinwiggles they want out of the design. Another sort of trick is that you can actually sort of raise your abstraction a little bit in terms of when you're looking at things like transactions. So you can actually use a sort of idiom where you would characterize a valid type of bus transaction, for example, we've got AHB here, as a sequence. So if you do that, you can then use this sequence in a kind of reusable way with parameters and whatnot, and you can do that, you can create checks for it, so this particular check is looking for an access to a particular lock register, and then we're actually saying, well, that must cause a lock bit to go high or a lock output to go high on the duct. So that's quite a useful, I would say it's pretty useful in terms of coverage, and you can actually then take it a little bit further and you can put together sort of little sequences, compose these sequences together, and you can say, well, can I cover this sort of magic access sequence over a bunch of registers with a particular string dead ABBA or something, and can we open up a secret password with that? So that it's quite useful, and you can raise the abstraction a little bit on these formal properties by encapsulating things in sequences. That's quite a useful little idiom that you can use. Another way that you can sort of raise abstraction is to basically create an FSM model which doesn't necessarily exist inside the DUT. It's a kind of higher level concept of the DUT state, which can then, it then promotes a more meaningful and interesting dialogue with the design team, let's say. So the example of this is that recently we had a project where you have a number of state machines in there, and we were doing checks on a design under test, sort of a bit of legacy code, and there were sort of essentially some implicit states and some high level behavior around the I/O of the block, which was really characterized in a table that the verification engineer captured. He then encoded that up as being a sort of abstract state machine. Then the properties and the discussion with the design team was actually a lot simpler by having this sort of high level FSM. And sometimes that, looking at the code, we said, well, actually, if this is equivalent, this is maybe a good proxy for the design restructure. Another point, again, you probably see this quite a lot, is that sometimes you run into the issue of writing properties. If you're writing very, very complex properties that's spanning a time period, and if you've got pipelined in stuff going on, so if you've got a pipeline protocol and you've got some handshaking in it, if you then sort of think about out of the box a little bit, quite often it's a lot easier to use some helper code to actually write the properties from that. So we've got something here which is a pipelined request grant protocol, and a simple counter on these requests and grants can then lead to some very simple properties on that. Okay. So then we asked the question about, well, formal is, I think Harry sort of said before, is this magic bullet? Well, there are some pitfalls with formal. First of all, you end up with some incomplete bounded proofs when you're running out of CPU time. You don't necessarily know when to stop because you don't really know how far you've got. A big one is if you have some faulty or incomplete constraints, you will get false positives potentially out of the tool. It can't find a counterexample because it isn't able to search the whole of the legal space. And also, again, I think Harry touched on this point earlier, is that some design structures just don't work well with formal. So obviously we need to use simulation to help us with this. So first of all, you can actually cross-check your constraints in simulation. You can cross-check the design understanding because you have a different mindset. Simulation is definitely a different mindset, different set of skills from formal. You can actually collect coverage metrics in a formal environment by using this sort of replay technique. And then you can go for those things that which you can't really tackle in formal. So it's a complementary approach. And you know, obviously, clearly, we're not replacing simulation with formal. Just a couple of slides on the sort of the formal replay flow that we developed in-house. I think there's some tools do support this, and I know that the old Cadence IEV tool did have this, mainly to produce waveforms for sort of witnesses and counterexamples. That was part of the internal mechanism on it, but it could produce you with some tickle scripts to do a simulation replay. So the rationale behind this is that when we're following a coverage, a code coverage regime that we have to provide for our customer, then creating the stimulus to exercise some of these coverage holes can be extremely time consuming. It normally happens towards the end of the project when you've got all the other stresses going on. So the concept of formal replay is to connect the two worlds of formal and dynamic simulation. So basically, you are storing your cover traces from the formal tool, from the IP or device level properties, and convert them into simulation results. So you get a VCD file, and then we transform that into a test bench, and we replay those in simulation. So there's two areas we target. The automatic covers, so we get a code coverage report from the tool. We look at those holes that we have in it that we know are reachable, and then we generate some waveforms to fill those, just replay those in the simulator. Another one is, potentially more interesting, is that you have some manual covers for sequences that are manually written for very specific, interesting corner cases that are quite hard to reach in simulation. And it's actually quite, generally speaking, it can be quite easy to write a cover sequence to hit an interesting point, FIFO overflow or error condition or whatever, and you can get a good waveform for that sort of stuff. Here's just showing you how we transform a ICCR report into a bit of SVA, which is our cover sequence. And here's a picture, because I think I'm very mindful of running out of time. Mike's there with the microphone, of just our flow. So basically, it's a combination of tickle and VTran that we use to go to wiggle, and then we go to point into the test bench. The test bench is invisible here, I think. So yeah, we have this flow. So the conclusions are: integrate FV into your verification flow. It's an absolute no-brainer. We have had so much return on investment, as they say, from this approach. Be careful not to neglect your covers. Try to raise abstraction if you can in your approach, and run those assertions in simulation as early as possible. We see from my experience, we see so many times when we see some dodgy assumptions that are made in the FV that are disproved in simulation. And then I think you need to judge the return on investment, so you always need to put a timeline on some of these formal activities. Take advantage of the push-button apps that you have in your tools, and drive a cultural change in your company. So make formal normal in your company.
Thanks. Thank you very much. Actually, it's quite a common story. Those who do adopt formal say it's the best thing they did, and then the other half of companies say how hard it is to adopt formal. So those who do make the journey.
I don't think it's easy. I don't think it's that easy.
Yeah, but once you're there, you can see the value. We have time for one question. Actually, can I just, did you ask one earlier, Anthony?
Hi, Anthony Wood, Imagination. You mentioned about ROI. I just wondered if you could just sort of break that down a bit. Where do you think you get the ROI there? Because you're obviously running simulations anyway. I understand that you're trying to hit holes, but yeah. Where is it?
I think the ROI is in terms of improving the quality before it hits the simulator. I think that's it, because we have those, you get those early sort of things, oddities. Does it really match the spec? Is the spec right? And you have those conversations much earlier. I think that's the big gain from my experience.
Okay, brilliant. Well, thank you very much, Steve. Thank you.